Let's look at problem E1. Here we have a mass sliding on a plane with some viscous damping between the mass and the plane. We're asked to find the transfer function relating the velocity of the mass to the input force. The first step in solving this is to draw an equivalent schematic such that it becomes more apparent how these two mechanical elements are connected. We find that the two masses share a common flow, and thus the total effort that is exerted on the system will be equal to the sum of the individual effort or forces presented by both the mass and the viscous damper. So we can write force is equal to impedance times velocity, but the impedance here is the sum of the two. Remember that when we have two elements connected in a common flow configuration, their impedances add. So we write Zm plus Zb is equal to V1. We go ahead and express the transfer function as V1 over F sub u, and now we can express that as 1 over the sum of the impedances. Our final step is simply to replace those two impedances variables with the actual impedances. So S times M for the mass and B for the viscous damper. Our final step then is just to format this into a standard form. We bring out 1 over B and we write it in a normalized form, S over a corner frequency or pole frequency plus 1. We find that the pole frequency is equal to B over M. Note that we could also have expressed the denominator as 1 plus S times tau, the system time constant, where tau is equal to M divided by B. For this first problem, let's take a couple minutes and answer the question of what is the significance of the transfer function? What can we learn from it? So here I've listed 3 or 4 things. So first one, A, is let's look at how the system responds to very low frequency, specifically for DC. In other words, if the forcing function f sub u is equal to some constant f naught times e to the st, remember that's our general form of excitation, but in this case where s is equal to 0, in other words, the external force is simply a constant f naught, then by plugging in s equal to 0, we find that the transfer function evaluates to just 1 over b. And remember, the transfer function scales the stimulant as it passes through the system, and the response is that scaled value of the input. So in this case it's f naught over b. This makes a good bit of sense if you think about it. Eventually the force exerted by the viscous damper will be equal and opposite to the current velocity that is being exerted by the external source, and thus there will be no remaining net force available to accelerate the mass any further. Okay, second thing we can learn from the transfer function is we can glean the differential equation. So in this case we simply cross multiply, and every time we see the variable s, we will replace that with the derivative dt, and wherever we see v1 of s, we'll replace it with v1 of t, and f sub u of s we'll replace with f sub u of t. And so this is another way to quickly arrive at the differential equation for the system. Third, we can assess the natural response of the system directly from the transfer function. Specifically, all we need is to look at the roots of the denominator, in other words, the poles of the transfer function. We're not looking for the exact solution, we're just looking for the functional form, meaning like is the natural response sinusoidal, what's the frequency, is it an exponential decay, is there a constant term, those types of things. And by the natural response, what we mean is if you wind up the system, say by giving it some initial conditions, and you don't force it, so you've turned off any external excitation, so f sub u is not there, and you just watch the system kind of wind down and come back to a rest on its own. Basically it's dissipating that initial energy that's part of its initial condition. What's the characteristic, what's the form, time domain form of its responses? And this will be true for a linear system, it will be true of all the responses, all the velocities, all the forces. If it's an electric circuit, it will be all the currents, all the voltages. Okay, we can find that simply by determining the poles of the system. In this case, there's only one pole. It happens to be at omega p. And so that tells us that the natural response will have it included in its form will be e to the omega p times t. In other words, e to the st, where s is equal to omega p. I should say minus omega p because it's a negative. The pole is really at minus b over m. So it's an exponential decay. This is a first-order system, as we would expect. The v sub naught, capital V sub naught, just simply is a placeholder for some constant that we're not determining here, but it would be determined based on initial conditions, like if you initially started the system out with the mass traveling at 10 meters per second, then that would be v naught. Okay, fourth, we can also draw the step response for the system. And this comes by combining A and C. So in other words, the step response after time 0, it's basically a constant input, just like what we considered in case A. But since it has been sitting at a value of 0, the input, forever, up until time 0, there is going to be a response in the output. In other words, it has to go from being at one steady state value, being driven by 0 force, up to being driven by some non-zero force. What we do in this case is we use s equals 0 to tell us, the transfer function value to s equal to 0, to tell us what the final asymptotic value of the step response will be. So in this case, the asymptotic value is going to be f sub 0 over b. That's what we found in part A. And then we take the natural response that we found in part C, and we say, okay, the way that the system is going to move from being at an initial condition of 0 and a final condition of f sub naught over b is it's going to transition between those states via a transient response that has the characteristic of e to the minus t over tau, or e to the minus omega p times t. And so it turns out it's a 1 minus e to the minus t over tau type expression. We can also look at the frequency response of the system. And in this case, when we plot that, we see that it is a low-pass filter response. In other words, it passes low frequencies, but at higher frequencies above omega p and much, much greater than omega p, it essentially attenuates the response by, the response is attenuated by a factor of 1 decade per decade. So if you go up a factor of 10 in frequency, the response will be 1/10 of what it was a decade below. And you can try any frequency. You can say, let's excite this system with 10 sine omega pt in this case. So we'll just pick that corner frequency. And we evaluate the magnitude and the phase. And to find the steady state, in this case the asymptotic steady state, not transient, how it got there from 0 to its final state, but once it gets there to its final state, the steady state response is simply a scaled version of what we excite it with, and the scaling is the magnitude of h, as you see here, and the phase, the shift of that sinusoid, is the argument of, or the angle of the transfer function evaluated at that frequency. Now let's look at 2 application questions. First, what is the electrical analog to the mechanical system of problem E1? Well, let's begin by listing the elements, the mechanical elements from problem E1, and finding their electrical equivalent. So the mass's analog is the inductor, the viscous damper's analog is the resistor, the effort or force source has an analog of a voltage source, and the configuration mechanically is common flow, meaning velocity of the mass is equal to the velocity of the viscous damper, and on the electrical side this translates into common current or series connection, where the current through the inductor is equal to the current through the resistor, so these are in series. So now we can draw the inductor and the resistor in series, and to these 2 elements is applied an effort, which is a voltage source. We can go through the same procedure to arrive at the transfer function, and we see that it has an identical form as that of our problem E1, where R replaces B, and our corner frequency or pole frequency is now R over L rather than B over M. Finally, let's look at this second application problem. Here we have a spring and a viscous damper. They're drawn in a bit of a strange manner. But we note that as we move the spring by grabbing onto the handle to which is applied the force F sub u, the plate that is coupled to the ground through a viscous coefficient moves equally. So in other words, they share a common flow. And so we can redraw this in a more standard schematic form of the spring and the viscous damper appearing in quote-unquote parallel, really being in a common flow, which is really an electrical series connection. So the total force, F sub u, is equal to the sum of these individual forces. And each of those forces, F sub k and F sub b, are themselves equal to their respective impedances times their respective velocities. So we have F sub u is equal to the sum of the two impedances times the velocity. We then solve for the transfer function, that is the velocity divided by the external force F sub u, which gives us 1 over the sum of the impedances. We substitute in B and K over S. We multiply through the top and the bottom by S over K. And that gives us our final result, which is S over K divided by 1 plus S over omega p. We compare this to our previous example or problem E1, where we had 1 over B rather than S over K divided by a similar denominator. The omega p in this case is different than the one in problem E1. Here it is K over B, and in problem E1 it was B over M. And when we think about this, we realize that at low frequencies, the system behaves as a spring in this case, whereas in problem E1 at low frequencies, the system behaved as a viscous damper. The last part to this application problem is to find the electrical analog. So we replace the spring with the capacitor, the viscous damper with the resistor, and the external force with a voltage source. Because it's a common effort configuration, these three elements are going to be in series, and we arrive at our very familiar RC filter. We express the transfer function as effort divided by effort. We express the transfer function as effort over the flow, which results in 1 over the sum of the impedances. And we resubstitute R and 1 over SC for those impedances, multiply through by S times C, and we arrive at an analogous result, which is SC divided by 1 plus S over omega p. And here omega p is 1 over RC, which is analogous to K over B for our mechanical system.